Welcome back to Differential Calculus. In this video, we're going to be talking about properties of infinity, most of which we've actually already talked about before, but now that we have the vocabulary of limits and infinite limits at our disposal, we can put some of it into a new light. Let me get my head out of the way and I'll show you what I mean. We've established previously that infinity is the least upper bound of the set of all real numbers. That is to say, first of all, that there is no real number which is as large or larger than infinity. Infinity is a larger number than every real number. And secondly, because infinity is the least upper bound, it must be the case that there is no real number which is an upper bound of R. Because every real number is smaller than infinity, if there was a real number that was an upper bound of the real numbers, then that would force infinity to no longer be the least upper bound, which is what we said is not going to happen. Right. Likewise, negative infinity is the greatest lower bound of the real numbers. Same idea. There is no real number that is as small or smaller than negative infinity, and there is no real number which serves as a lower bound of the real numbers. Otherwise, negative infinity would not be the greatest of the lower bounds. If you go further into the study of mathematics, beyond what we teach at the community college level, you will start to see some other facets of this same idea come up. It turns out that there are some applications where having more than one infinite value as an upper or lower bound of the real numbers is useful. That branch of study is called real analysis. It turns out that there are some applications where considering the set of all the real numbers plus infinity and negative infinity is a useful thing. That branch of study is measure theory and probability. But for our purposes, remember that infinity and negative infinity are themselves not real numbers. And that fact is a lot of the headache that comes along with this lesson. A lot of what we're looking at in this video and the last couple and the next couple is dealing with the fact that we want infinity to be the answer, but infinity is not the real number. So we can't say equals infinity. It doesn't make sense. We can't say multiply by infinity. We can't say divide by infinity. Those things don't make sense. They're nonsense. Well, for some of those at least, by the time we're done with this lesson, we'll find a way to make them work anyway, but they're nonsense. The other property that we have is that the limit as x goes to 0 of 1 over x, when you look from the positive numbers, gives you positive infinity, and the limit as x goes to 0 from the left, from the negative numbers of 1 over x, gives you negative infinity. That's what we know about infinity. And even at that, it's quite a bit. From those claims, from those definitions, we were able to come up with the fact that the real numbers are, in fact, the interval from negative infinity to infinity. We were able to come up with this idea of vertical asymptotes which occur when the limit is either infinity or negative infinity. And you can have one-sided vertical asymptotes. You can have vertical asymptotes that split. You can have vertical asymptotes that do the same thing on both sides. Those are all perfectly valid. The interesting thing that I want to look at in this video is the question of what happens when x tends towards infinity instead. In a future video, I'm going to look at that from the very foundational definition point of view. For right now, I want to think about that qualitatively. If I think about a set of coordinate axes, I know that the limit as x goes to something equals infinity is what happens if I have a curve that looks like that. As x goes to 0, f of x goes to infinity. And so the idea that I want to explore here is, what if I took a mirror of this? What if I reflected this about the line? That's the wrong color. That's the one I want. What if I reflected this operation about the line y equals x? Then I would instead have a curve that was looking like this. And this curve would represent what happens as x goes to infinity. And what we're seeing come out of this is that y goes to 0. And graphically, that's kind of how I take my definition of x goes to infinity. If I look instead back at this 1 over x graph that we've looked at previously, get some space here. Right? Y equals 1 over x. If I sketch out some coordinate axes, we know that this curve looks something like that. One of the properties of this curve that we haven't looked at previously is that it is an odd function. It is symmetric about the line y equals x. Y of the opposite of x is the same thing as the opposite of y of x, the opposite of 1 over x. And so with that, and the properties we were just thinking about, we can use this as our definition of positive and negative infinity. We know that it is true that as x approaches 0 from the right, y approaches positive infinity. And as x approaches 0 from the left, y approaches negative infinity. And because it is symmetric, I should be able to swap x and y. As y approaches 0 from the right, x approaches infinity. And as y approaches 0 from the left, x approaches negative infinity. And since I'm swapping things anyway, it should be that just as I can choose my horizontal range first, these should work in symmetry. I should be able to approach that in the other order and say that as x approaches infinity, y goes to 0. And as x approaches negative infinity, y goes to 0. And when you look at the graph, that's what happens. As x goes to infinity means as we are getting x to be larger and larger and larger values, the value of y is coming closer and closer to 0. As you are looking at x going to smaller and smaller values, the value of y is coming closer and closer to 0. Let's try writing that in characters that actually look like English words. The limit as x goes to infinity is going to define a horizontal asymptote for our graphs. And that's the way that we're going to interpret it for this video. If I jump over to Desmos here, you can see that I have sketched out the function f of x equals x plus 1 over x minus 3. This function is a rational function. It's the kind of thing that you've analyzed in previous courses. We see that this graph has a vertical asymptote at x equals 3. That occurs because the denominator, on this side of me, the denominator right here, x minus 3, is 0 when x is equal to 3. Ergo, vertical asymptote. One of these days I'm going to get used to being in front of a blue screen. Today is not that day. The other thing we notice is that there is this horizontal asymptote right there on the line y equals 1. And you may remember from a previous mathematics course looking at the fact that the coefficients on x in the numerator and denominator are both 1, and that having something to do with it. If I change this equation just ever so slightly, and instead of x plus 1 over x minus 3, I wrote it as, say, 5x plus 1 over x plus 3, all of a sudden that moved the horizontal asymptote from y equals 1 to y equals 5. If I change it from 5x plus 1 over x minus 3 to 5x minus 1 over 2x minus 3, not 22, just 2. Now all of a sudden, that changed the y asymptote to 5 over 2. That changed the vertical asymptote as well, but I'm not nearly so worried about that. And so we have this feature of when you have a rational expression where the numerator and the denominator are polynomials of the same degree, you can use the coefficients on the numerator and denominator to come up with the numerator and denominator of the constant value that gives your horizontal asymptote. Nothing new there, although it may have been a while since you've thought about it. The thing that I want to look at that is going to be a little bit different is what happens if that denominator is more involved than just being a polynomial. Now we've really got something interesting. The numerator has stayed the same, 5x plus 1. The denominator has not. I now have the square root of x squared minus 9. Some of the things to notice here. In the region that I've highlighted in pink, between x equals -3 and x equals +3, this graph does not exist, right? That is where x is, well, equal to, I didn't really highlight, but less than, right? If the denominator here, x squared minus 9, is less than 0, then when you try to take the square root, bad things are going to happen. So there's an entire region of the graph that doesn't exist. Not only that, on the right side, we have an asymptote going to positive infinity. On the left side, we have an asymptote going to negative infinity. And on the right side, our horizontal asymptote tends towards y equals 5. And on the left side, our horizontal asymptote tends towards y equals -5. One of the things you will notice here is that, yes, there is an intercept here where it is equal to -5. The function is equal to -5. If that goes up to be slightly larger before well off screen coming back down, and there is a maximum somewhere further along on the line than where my screen has gotten to. That's another thing we will study in depth a little bit later on in the course. The important thing is noticing that the horizontal asymptote on the left and on the right are tending towards different values. I happen to have chosen this function so that it is the same value, just positive or negative, but even that doesn't have to be the case. If I take this +1 that was in the numerator and I move it outside, then all of a sudden that shifted my horizontal asymptotes both up by 1. And so you can have horizontal asymptotes that take on different values, and it is perfectly reasonable and definitely a thing that we can look at. So that's what I want you to look at for today. The function f of x equals 9x minus 5 all over the square root of x squared minus 5x plus 2, all minus 1. After you have graphed it, I want you to use the graph to approximate the limit as x approaches positive infinity and the limit as x approaches negative infinity of this function. Right. Play around with that for a while. First of all, to get used to thinking about a graph. Second of all, to think about how to graph things using computer software. One thing I'm going to encourage you, if you can't quite tell where the asymptotes are taking you, try zooming out. Dig into settings, see if you can figure out a way to zoom out in the x direction while zooming in the y direction. Will give you a much nicer graph. Right. So there's something for you to play around with. See what you can do with that, and I'll see you in the next video.